Now, prior to this, we've been using a bunch of different strain gauges to measure our strain in a particular material due to the force, the stress that's been applied to that particular material. Now we'll be using something else. We'll be using something called a load cell. Now, a load cell is something that we use to measure force or weight. And there's lots of applications around that we use load cells in, from weighing the weight of a car or weighing the weight of an engine block within a car or an aircraft or something like that. We can use them for condition assessment. I've used them for condition assessment of concrete using a penetrometer, measuring how much force I can apply when I'm pushing a probe into concrete. We use them within the medical realm of measuring the weight of equipment or of patients, because the amount of drugs and the efficacy of those drugs will change based on the weight and size of patient. And measuring the weight of things like powders, for example, when we're filling bags up with something or we're mixing something. All different areas that we use load cells because we're wanting to measure the force or a particular weight across something. Now, you might say, oh, I thought we were doing this with strain gauges. And there's some similarities and some differences between load cells and strain gauges that we'll pick up in a moment. But let's look at the four main types of load cells that are out there. Our first type is a strain gauge type of load cell. And so you can see very quickly that there are some similarities between strain gauges and load cells, because one type of load cell actually uses strain gauges within it. Essentially what we have is we have a block of metal that's been machined out or precisely made, and that will contain typically a few strain gauges within it. Maybe 4 strain gauges, maybe as many as 16 strain gauges. Now, typically these are connected up into our Wheatstone bridge format to allow us to do some compensation for things like temperature, but allow us to also amplify the force that we're actually seeing in there and creating a larger force so that we can more accurately determine what weight is being applied or what force is applied here. Now we've got a bunch of different types of these, from our S1 that's above, and that's for measuring larger forces. In this case, that one can measure up to 500 kilograms, to our really small ones just here, which are shown how they work over here, which have a number of strain gauges either in the middle or in each of the corners, and they're for smaller weights, maybe up to 10 kilograms or so. Well, let's move on to our hydraulic load cells. And our hydraulic load cells essentially have a force that's pushing down from above that pushes against a piston, and that piston applies pressure to a diaphragm. And that diaphragm, based on how much force is applied, changes the amount of pressure in the liquid that's below. Now, we put then a pressure gauge in there, in this case an analog pressure gauge, but it could be a digital pressure gauge, in line with that liquid there, and we can measure the change in pressure of that liquid. And as that liquid changes in its pressure, we can measure how much force and infer how much force has been applied to cause that change in pressure of the liquid. Now, our pneumatic load cell, hydraulic uses liquid, pneumatic uses air, and our pneumatic load cell works in a similar sort of way. So we have compressed air coming in, that's regulated down to a particular pressure, for example, 10 psi. We apply our force to that unit there, that load cell unit, and then we measure the pressure coming out of this unit. And in this case, it might be 20 psi. And so our force being applied has actually changed the pressure within that unit, and we can actually measure the change in pressure within that unit. And so a higher pressure corresponds to a higher weight or a higher force that's been applied here. Our final one that we'll look at is our capacitive load cell. Now, within our capacitive load cell, essentially we have 2 metal plates, and those metal plates form a capacitor. Now, you remember a capacitor is something that can store an electric charge back from first year. Now, if those plates are bigger, we can store a bigger electric charge. And if those plates are closer together, we can store a bigger electric charge as well, compared to if they're further away from each other. Now, essentially what we can do is we can couple our weight or the force being applied to control how close those plates are together to each other. So if we've got larger force applied, those plates can be closer together. Or if we've got a smaller force applied, those plates can be further away from each other. And so we can directly measure the capacitance of this load cell and based on that, infer the force or how much weight that's been applied here. And that might be the question for you, okay, which one do I use? And they've got different pros and cons around them. So our hydraulic load cells, for example, are really good for high capacity applications. For example, if we're trying to measure a semi-trailer or a car or something quite heavy. And they're quite good for harsh environments, maybe explosive environments and things like that, where we don't want electronics around them. Maybe they're environments with lots of water around them, where we don't want that electronics around them that could get damaged, or a spark that can be generated that will make something blow up. Likewise, our pneumatic ones are good for those hazardous or dangerous conditions. They can be quite high capacity and have good resistance to things like shock and vibration. In comparison to our strain gauges, which will probably, a bit more of that vibration will be induced into the system. But our strain gauges are probably our most common form of load cells, also very low cost load cells in comparison to some of those other ones, and very accurate ones. Likewise, our capacitive ones are very accurate, but also low power ones. We're not using nearly as much power within our strain gauge compared to our strain gauge ones within our capacitive ones. So there's pros and cons of each of these. And you also might ask the question, hang on a sec, well, what's the difference between a load cell and a strain gauge, considering that one type of load cell can contain a strain gauge? Well, essentially strain gauges measure strain. And so we apply a strain gauge to a material that we're looking for the amount of deformation that material's having. In our load cell, we want to measure a force or a weight that's been applied to it or across it. And so we're not interested so much in that actual deformation anymore. We're interested in the force. And one of the ways that we can measure that force is through deformation. Now, strain gauges are typically cheaper, have smaller ranges that they can operate over, but are more sensitive. Whereas our load cells, because we've essentially attached a strain gauge to a block of metal and then we're applying forces to these blocks of metal, they are more expensive, but they also have higher measurement ranges they can operate over. For example, hundreds of kilograms for some that look like this. So it really depends on what we're trying to measure. If we're trying to measure material deformation or the strain that's actually on the material, we want to use our strain gauge. If we want to measure force or weight of something, we want to measure using our load cell.